So recall that when we are trying to evaluate an integral to find an antiderivative using a substitution, what we're looking for is some small function that's being functioned again. And what we expect is whatever that inside function is, whatever we're going to let our u be, that the derivative of u is also a factor in the product that makes up our integrand. And just a hint, that outside function, the function that's happening to the inside, so the outside function, is probably one of the functions from your function booklet. So if you kind of have a running catalog of those functions, what were there, 11 functions in your head, probably one of them is going to be the outside function. Whatever's getting that function is going to be your u. So if it's helpful, it's very frequently something that's inside parentheses. So here I have an integral. I want to evaluate this integral. I want to find an antiderivative. And I do happen to have an expression inside parentheses. So look at that 7x minus 2. What's happening to 7x minus 2? 7x minus 2 is getting cubed. Do I know how to take the derivative of some function getting cubed? I do. I'm going to bring the 3 down and I'm going to... No, do I know how to find the antiderivative of something getting cubed? Yeah, I'm going to raise the exponent to 4 and divide by the new exponent. So that's one hint that our u in this case is going to be u equals 7x minus 2. The good news is in your textbook, your first several homework problems, they'll tell you what to use as your u, so you can just practice not accidentally putting a second variable in your integral. And then once you sort of get the hang of it, that's when you'll have to figure out your own u. All right, so if I let u equal 7x, then du equals 7 dx, du over 7 is equal to dx. And I'm going to write my new integral. So it's the same as the integral 28 u cubed times what's dx. I'm going to replace dx with du over 7. So notice my new integral, that 7 and the 28 are going to cancel to leave behind 4. 4 I might factor out to the front, but it's not required. It's going to be 4 times the integral of u cubed du. I can find the antiderivative of u cubed. So here's the 4, comes straight down. This is going to be u to the 4th over 4 plus a constant. And you can see that the 4's will cancel, and I'll have u to the 4th plus a constant, but it's going to be my job to put back what u was. So it's going to be 7x minus 2 raised to the 4th plus a constant. Remember, I can always find out if I got the right answer to an indefinite integral problem by taking the derivative of my answer. So here, if I come up here and I find d dx of 7x minus 2 to the 4th plus a constant, that's going to be 4 times 7x minus 2 cubed. And I'll have to use the chain rule, so multiply by the derivative of the inside is times 7 plus 0, because the derivative of c is going to be 0. This the 4 times 7 will multiply to make 28. 7x minus 2 cubed. If I take the derivative of my answer and get the original integrand, that means that my answer is correct. So here we go, 7x minus 2 raised to the 4th plus a constant. All right, here in this last example, we have a definite integral. You can still evaluate a definite integral using a u substitution. You're going to have the same process. You have one more thing to consider here, which is that this definite integral means find the area under the curve tangent x secant squared x from x equals 0 to x equals pi over 3. That means that the 0 and the pi over 3 are both x values. So I'm going to change this integral from having x's to having u's. I have to change the limits to match. And to change the limits into u limits instead of leaving them as x limits. So here, I could imagine, where could I put a multiplication dot in this problem? Well, that's tangent x times secant squared of x. Is one of those the derivative of the other? Conveniently, yes. So I'm going to let my u equal tangent of x, in which case du is secant squared dx. And now I can think of u as a function. If I plug some number into u, so u of 0, for example, is tangent of 0. So I'm going to make a new lower limit for this integral. So u of 0 is tangent of 0, which is 0. Can you see that behind the touchcast? And then u of pi over 3 is equal to tangent of pi over 3, which is equal to radical 3. So now I have enough information to rewrite this integral using only u's. So let me just write here that, I actually do this last step, which is that du over secant squared of x is equal to dx. There we go. Now I'm going to write my new integral. So my new limits, because I'm going to put u's in here, my lower limit is u of 0, which is tangent of 0, which happens to also be 0, but that's just a coincidence. My upper limit was pi over 3, but I want a u limit, so I need u of pi over 3, which is tangent of pi over 3, which is radical 3. And then I'm going to have tangent of x, which is u, times secant squared of x, times dx, but dx is du over secant squared of x. I can see here that my secant squared of x's are going to cancel. So my new integral from 0 to radical 3 of u du. And I'm happy to note that that has only one variable. I do, in fact, know how to find the antiderivative of u. That's just u squared over 2. I don't need a plus c here because this is a definite integral, so I'm going to have u squared over 2, and I'm going to evaluate that from 0 to radical 3. So that makes radical 3 squared over 2 minus 0 squared over 2, which is radical 3 squared is 3 over 2. 3 over 2.